All right. Hey, everyone. Welcome to today's lesson on hybridization. So, again, what we're trying to do kind of in these first few weeks of the unit is just really kind of build up your organic toolbox. And really, what's at the heart of organic is learning to analyze molecules, if you will. And so, this is going to be another tool in your toolbox that we're going to refer to as hybridization. What this really has to do with is kind of how molecules or how the atoms within molecules bond and how that kind of affects how those atoms are arranged to give the molecule certain shapes. So, just to kind of, I guess, give you a little bit of a preview as to how I'm going to go through the lesson, is for the front page of your notes, this is really going to be more of the conceptual side to hybridization. And I want to give you a heads up that a lot of this, it may go over your head, which is totally fine. You really don't dive quite deeply enough into what are called orbitals in Chemistry 1 to really fully grasp this. But I'm still going to just present it to you just for exposure's sake. And if it, catches your interest, this might be something cool that you enjoy seeing the behind the scenes of. But this first page is the conceptual side, and so it's okay if not everything fully makes sense. Then, what I'm going to do on the back page is this is where I'm really going to get down to the practical. It's like, okay, even if some of the conceptual went over your head, what do you actually need to be able to do with this for the purposes of our class, and oftentimes for the purposes of an organic class in college? And again, a lot of this is really just helping to take off some of that shock factor. And that way, if you do see organic again in your future, that you're not just completely thrown off by it, that you've heard some of these terms, you've practiced some of these things before. But the back page is really what I want you to be able to do and take away from it. This first page is just a little bit more of the background, a little bit more of the conceptual. And so I can challenge you if I could. I know when we're learning through video, sometimes it's tempting to just kind of tune out or want to fast forward, but I encourage you to approach this with an attitude that's willing to learn, wanting to glean something, and we'll see if we can get through this together. All right, so here we go. So, where this kind of topic originates from is it is essentially one way to view the geometry or the shaping of the atoms within a molecule. Now, what you would have learned back in Chemistry 1 is what was called VSEPR theory, VSEPR, which stood for valence shell electron pair repulsion. And that would have been kind of associated with this little chart right here, which would have been your different geometries: linear, trigonal planar, tetrahedral, trigonal pyramid, bent, kind of all that good stuff. And so that's one theory that kind of explains how the atoms within molecules take their shapes. But another theory that kind of goes along with that is what's called the hybridization model. So it says VSEPR theory is useful for explaining the shape of molecules, but it does not explain how an atom's orbitals are affected by the formation of bonds. It says that's where the hybridization model comes in. So when we're talking about orbitals in this word, what we're referring to is those three-dimensional kind of wave particle dual shapes that the electrons occupy, or in which they exist within the atom. Back in Chem 1, this would have been the section on electron configuration, where we learned about s orbitals, d orbitals, p orbitals, f orbitals, where we would have coded for an atom's orbitals like 1s1, 1s2, 2p6, kind of all that good stuff. That may be quite the throwback. But it's these orbitals within the atoms themselves that affect the way those atoms bond or overlap with other atoms. And so, what bonds really are when these orbitals actually overlap between atoms. And so what we're going to look at is kind of the different ways that they do that. Now, what happens oftentimes is that the orbitals, they will oftentimes do what's called hybridization before they overlap. And if we think about that word hybrid, typically that means it's a combination of things. So, like when we were on a quote hybrid schedule during COVID, you would have spent part of your days doing virtual school online, and a few other days a week you would have been in person on campus. So, it's kind of like a blend or a mix of both. And so, what hybridization does is it kind of blends or mixes those orbitals to create new hybrid orbitals. Now, there are going to be kind of three types of hybridization. There's sp, sp2, and sp3. And so where they get those names is from which types of orbitals that they mix. So in sp hybridization, you're mixing an s and a p orbital. And so what the rule of thumb is that however many orbitals you mix, that's how many new hybrid orbitals you form. And so the new hybrid orbitals kind of look somewhat like an S, somewhat like a P. So they're kind of big and balloony like the S, but they've also kind of got that two half kind of peanut shape like the P orbital. And then what gets left behind are kind of two p orbitals that are unhybridized. These are going to be the ones kind of right here at the end. These are unhybridized orbitals. All right. Now, if we go to sp2, that's mixing an s orbital and two of the p orbitals to generate kind of three new hybrid orbitals. And then sp3 kind of mixes the whole set, an s orbital and three p orbitals, to generate four new hybrid orbitals. Now, the number of new hybrid orbitals formed, 2, 3, and 4, actually corresponds with some of the different electronic geometries you would have learned about in Chem 1. Linear, 2 regions, trigonal planar, 3 regions, and tetrahedral, 4 regions. So when we were using that chart, you may not have noticed, but it actually has a little SP, SP2, and SP3 kind of little note on hybridization actually written into that chart. So those kind of line up, if you will, with VSEPR theory. Now, what you can do with those hybrid and unhybridized orbitals is overlap them to form different types of bonds. So what that brings us to is kind of this new vocab term of a sigma versus a pi bond. So a sigma bond is symbolized with a little Greek sigma symbol, and a pi bond is symbolized with the Greek symbol for pi. A sigma bond is formed from the overlap of those new hybrid orbitals. So those are the ones we kind of just drew like that look a little bit like an S and a little bit like a P. And then our pi bonds, those are formed from the overlap of those remaining unhybridized p orbitals. So those are the ones that were not blended with anything and that kind of look like that. So if we kind of take a look, the sigma and pi bonds are kind of what's behind single, double, and triple bonds, if you will. So in a single bond, you have one sigma bond and 0 pi bonds. An example of that is the molecule ethane, that's 2 carbons with just single bonds. And so each carbon here, this is what we would refer to as sp3 hybridization. So each of those carbons has mixed an s and 3 of its p orbitals to kind of generate 4 new hybrid orbitals. And it's that overlap kind of right here of two of those hybrid orbitals that gives us this single bond in between that we would call a sigma bond. A double bond is actually made of one sigma and one pi bond, if you would. An example of that is ethene. So we've been learning functional groups. So this is in the alkene family. So what you'll notice in the center, this is kind of representing sp2 hybridization. And what that does is they've mixed most of their orbitals, but each of those carbons would have one unhybridized p orbital as well. So it's that unhybridized p orbital that actually forms that double bond. And then the single bond, that sigma bond, is there in the middle. And I'm realizing now I kind of got my illustrations swapped here. So I'm sorry, the colored ones should actually be flipped if you want to draw an arrow. So here's that one sigma bond. And then here is the interaction between those unhybridized p orbitals that actually forms that double bond. So double bonds are actually not twice the strength of a single bond just because they're formed from different orbitals. Then last but not least, if we look at sp hybridization, that represents a triple bond. That is composed of one sigma and actually two pi bonds, since each sp atom would have two unhybridized p orbitals. So again, that's kind of this diagram here. So here you've got your sigma bond. You've got kind of this overlap here of this one set of p orbitals, and then another overlap here of another set as well. And so that's what creates kind of the triple bond like you would see in ethine. All right. So I know that's a bit much. So take a deep breath. And now let's talk about the practical side. If that didn't quite make sense, that is a-okay. Here's what you kind of need to be able to take away from it. All right. So it says for practical purposes, here's what you need to know. So when it comes to hybridization, if the atom is involved in only single bonds, then you can identify it as sp3 in its hybridization. If the atom is involved in at least one double bond, it's going to be sp2. And then if the atom is involved in at least one triple bond, then it's going to be sp in hybridization. So if you want to pull out a couple of highlighters, this is where we'll kind of start practicing a little bit. And this question comes up all the time in organic classes. Identify the hybridization of this atom. Again, I know we're just kind of doing the basics today, but later on, like the more chemistry you know, this hybridization can actually be a really helpful tool in helping like predict some molecules' behavior and just kind of better understand how they work. All right, so we'll go ahead and assign some colors here. So we'll make our sp atoms. I'm just going to make those orange. If you want to go ahead and pull out your orange highlighter. We'll do sp2 atoms in yellow. And then we'll do sp3 atoms in blue today. Now, you'll notice that I've kind of left a note in parentheses here that says do it for non-hydrogen atoms. So we're going to be doing it for things other than H's, so like carbons, nitrogens, oxygens, kind of different things like that as well. All right, so got some little diagrams here from a website called Chemistry Steps. And so what we're going to go through and try is just to identify, the hybridization of the different atoms that we encounter. So we'll start with A here. And so we're going to look for things that aren't hydrogen and try to color code them based on their hybridization. So if we focus in kind of on this carbon here on the left, I'm going to start asking myself, well, what type of bonds is it involved in? This carbon is only involved in single bonds, so that's going to make it sp3. And so I'm going to go ahead and highlight that one blue there. All right, as I move down the line, I'm also getting another carbon here. This carbon, right here in the center, is also involved in only single bonds, so it's also going to be sp3 in hybridization. All right, I'll come to the nitrogen here. So the nitrogen just has a single bond to the carbon, and then those would also be implied single bonds to the hydrogen. So it likewise is sp3. But then we come to two carbons that both are a part of at least one double bond, and that's going to make them what's called sp2 in hybridization. So we ended up with 3 atoms that were sp3 and then 2 atoms that were sp2. And so that's really what you need to be able to do practically, is kind of figure out, what is their hybridization. We're just using the color code kind of for a shortcut, so you don't have to write this, in every time, but that's what those colors are meaning. All right, so let's look at C together right quick. So this first carbon we come to on the left, it is involved in a triple bond. So that's going to put us in kind of the sp category. Same for the next carbon. It's also a part of that triple bond. But then our next 2 carbons are actually part of double bonds. So they're going to be sp2 hybridized. And then our final 2 atoms, the carbon and the chlorine, are also sp3 because they're only involved in single bonds. So you can quickly kind of determine hybridization just by looking at the bonding in which that atom participates. All right, I'll go down and do kind of one more here. So these were all expanded Lewis structures where you've got all the atoms drawn out. But the same technique actually also works on these skeletal structures where our hydrogens and carbons are hidden. So again, we're going to follow that same line of reasoning though. If it's only single bonds, it's sp3, double bond, sp2, and then triple bond is sp. So what I want to be thinking about is, okay, where are my carbons in that molecule? So what we'll do is we're going to look for our carbons, which we know are on bends and ends. If it's a carbon that would just have single bonds, those are going to be our sp3 carbons. So I'll leave a little reminder of what that blue means. And there'd actually, let's see, be one more down here. And then if it's a carbon involved in at least one double bond, those are going to be our sp2 carbons. So here, 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 and here. And then also the oxygen is involved in a double bond, so it will be sp2 as well. All right, so that particular molecule only had sp2 and sp3 atoms. In just a second, I'll let you give it a try on the others. And just a quick tip on this particular drug molecule over here on the left, or particular molecule, bio kind of molecule on the left, is you've got this triple bond. Don't forget that there is a carbon on either side of that. So this would be sp, and then this would also be sp as well once you kind of get to that molecule. I know some of the bonds look a little bit funny as well. You can treat them as if they were just lines. So you can kind of pretend that this is really just kind of a line and treat it the same way if that helps you out. So you're really just thinking about it as being a bond to a carbon there. Since that's just single bonds, you'd also find an sp3 one there. It's just a slightly different way of representing the bond called wedge dash notation, which we'll eventually learn about and kind of add to our molecule toolbox. All right. So that's kind of the practical side of doing hybridization. I'll give you a chance to finish that for the remaining 3 molecules in a second. But let me go ahead and quickly kind of show you how to practically also do sigma and pi bonds. So sometimes you will be asked to kind of give a count as to how many sigma and pi bonds are within a molecule. Again, we don't really get into this at our level, but why it's helpful to identify those is that can help you predict like at what spot a molecule might react or make a certain change. But for the practical here, sigma bonds essentially are going to be a part of every type of bond. So single bonds count as 1 sigma bond. Double bonds count as a sigma and a pi bond. And then triple bonds count as 1 sigma and 2 pi bonds. So when it says count the number of sigma and pi bonds for each molecule, what I recommend doing first is kind of going through and marking all of your sigma bonds. So for example, if we go down to this molecule C, we know that every bond, single, double, and triple, involves at least 1 sigma bond. So this would be a sigma, 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 sigma. You kind of get the picture there. All right. Then what I want to go back and do is mark any pi bonds, which essentially is just the remainder of the double and the single, or the double and triple bonds. So I'd have 2 pi bonds in that triple bond and another pi bond in that double bond right there. But everything else that I've got marked in green, those would all be sigma bonds, kind of so on and so forth. So if I count the green bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, let me make sure I counted right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would have 10 sigma bonds. Then if I go back and count the pi bonds, that's 1, 2, 3. I would have 3 pi bonds. All right. I can also go back and do that for our first molecule, molecule A. So mark your sigma bonds first, which is if it's a single bond, that's the whole thing. If it's a double or triple bond, it's only 1 part. Now, here's where you have to be a little bit careful. Technically, that nitrogen up here is also bonded to 2 hydrogens. So don't forget to include those in your sigma bond count. That's kind of this area right here. And then we'll mark our pi bond as that other part of our double bond there. So if we give a total count of sigmas, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 sigma bonds and then just 1 pi bond there within that molecule. Also, just like you can do with the expanded Lewis structure, this works the same on our skeletal structure. You just have to be mindful of how many bonds to hydrogen there actually are. So don't forget that, for example, this carbon up here at the top would really have 3 bonds to hydrogen. So if it helps you, you're welcome to draw that out. Or you can just kind of keep track and say, okay, well, this carbon would have 2 bonds. So I'm just going to make a note that that's 2 sigma bonds that would have to hydrogen. Whatever helps you. I'll go ahead just for kind of teaching purposes and just put in those carbons and hydrogens. That way you can see a little bit more easily. Kind of erase my little notations here. All right, and again, remember that where I'm getting the number of hydrogens is just enough to make 4 bonds to each carbon total. So again, if you can do it without having to draw it out, that's fantastic. But if it helps you, feel free to sketch out those hydrogens. Then we'll go through and mark all our sigma bonds, which are all the singles and a part of each double. Gotta get all those hydrogens in. Ooh, there are a lot of them. All right, so let's see if I can count these here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Woo! Big old molecule there. All right, and then if we go back and mark our pi bonds, which are those other parts of the double bond, those are a lot easier to count. There should just be 3 of those present. All right. So now, if you don't mind, if you'll kind of pause the video, what I'm going to let you try is kind of these same 2 things, highlighting for hybridization and then counting the sigma and pi bonds for molecules B, D, and E. Once you try those, if you'll unpause, and I'll pop up the answers for you to be able to check. Alrighty, so thanks for pausing. Thanks for giving those a try. Again, this is just your first time, so please please be gentle on yourself as you're kind of checking your answers here. All right, so there's B. Again, the orange is sp hybridized, the yellow is sp2, and then the blue atoms are sp3. There are a total of 19 sigma bonds and 4 pi bonds. All right, here's molecule D. It sure does make it easier when everything's drawn out to count those sigma bonds. So there are 20 sigmas and 4 pi's. And then you've got your highlighting there to kind of match with your hybridization. All right, and then last one, molecule E. This was the doozy. Because all of those hydrogens were not drawn out, that's what my little markings mean here for how many sigma bonds would be hydrogens attached to those particular carbons. I think I double counted, but I think it should be 52 sigma bonds. And then the pi bonds, a lot easier to spot. You had 3 from double bonds, plus 2 from that triple bond, which gave you 5 total. All right. So again, if you've got questions, please don't hesitate to ask. We're just all kind of getting our feet wet with this, enjoying the process. The biggest things this takes is just a little tenacity, some attention to detail, and just a willingness to not give up. All right, but thanks so much for watching. Sure appreciate it, and hope you have a good rest of your day.